Hello everyone. Welcome to the classroom of Advanced Manufacturing Technologies for Welded Structures. Today, we will explore the fundamental knowledge of laser cutting and blanking. I am your lecturer, Zhou Xinghe. Laser cutting is a crucial processing technology in modern industry, widely applied in automotive manufacturing, aerospace, electronics, and other fields. Through this lesson, we will delve into the principles, classifications, equipment components, characteristics, and methods for optimizing process parameters of laser cutting. I hope that everyone will master this knowledge and apply it effectively in practical operations. Let's begin by outlining the learning objectives for this lesson. 1. Knowledge objective. Understand the basic principles and characteristics of laser cutting and become familiar with the components and functions of the equipment. 2. Ability objective. Learn to set and optimize laser cutting process parameters. 3. Quality objective. Develop a strong sense of standardization to ensure operational safety and processing quality. I hope that through this lesson, everyone will achieve these goals. Next, let's identify the key and challenging aspects of this lesson. Key points: principles, classification, equipment composition, and setting and optimization of process parameters for laser cutting. Difficult points: optimizing process parameters can be complex, requiring a comprehensive consideration of material properties, equipment performance, and other factors. We can employ methods such as experimentation and computer simulation to optimize these parameters and achieve the best cutting results. I hope that everyone can grasp the key points and overcome the challenges during the learning process. Let's start by examining the basic principle of laser cutting. Laser cutting utilizes a high-energy density laser beam to locally heat the material until it melts or vaporizes. The molten or vaporized material is then blown away by high-pressure gas, completing the cutting process. Characteristics: high precision, high efficiency, and minimal deformation. Application scope: it is widely used for processing both metal and non-metal materials, including stainless steel, carbon steel, aluminum alloy, plastic, wood, and glass. The principle of laser cutting may seem straightforward, but in practice, a multitude of factors need to be considered comprehensively, such as laser power, cutting speed, and gas pressure. Laser cutting can be categorized into the following types based on different processing methods. 1. Laser vaporization cutting, suitable for extremely thin metal and non-metal materials. It offers extremely high cutting precision, but operates at a slower speed. Primarily used for micropart processing. 2. Laser melting cutting, ideal for non-oxidizable or active metals like stainless steel and aluminum. It features fast cutting speed and good surface quality, making it widely used in automotive manufacturing and aerospace. 3. Laser dicing and controlled fracture, appropriate for brittle materials such as glass and ceramics. It provides high cutting precision with minimal material damage. 4. Laser oxygen cutting, suitable for oxidizable materials like carbon steel and titanium steel. It boasts high cutting efficiency and low cost, though an oxide layer forms on the surface after cutting, necessitating subsequent treatment. Different types of laser cutting methods are suitable for various materials and processing needs. You need to select the appropriate method based on the specific circumstances. The main classifications of laser cutting are illustrated in the figure. Laser cutting equipment consists of the following main components. 1. Laser generator, the core component that generates high-energy laser beams. Common types include carbon dioxide lasers and fiber lasers, each suitable for different materials and cutting thicknesses. 2. Cutting head, responsible for focusing the laser and controlling the cutting direction. equipped with focusing lenses and nozzles. 3. Auxiliary equipment, including the cooling systems, gas supply systems, and smoke exhaust and dust removal systems, all of which ensure the smooth operation of the equipment. 4. Control system, responsible for programming and controlling the cutting path. Modern equipment typically employs numerical control technology to achieve complex trajectories and high-precision cutting. Understanding the components of the equipment and their functions helps us better use and maintain the equipment in practical operations. What are the characteristics of laser cutting? Let's learn together now. Laser cutting has the following characteristics. 1. Narrow slit, minimal deformation. The laser beam energy is highly concentrated, resulting in a slit width of only 0.1 to 0.5 millimeters. The thermal influence is minimal, and workpiece deformation is negligible. 2. High precision, fast speed. Cutting precision can reach plus or minus 0.1 millimeters, and the speed is several times higher than traditional methods, making it especially suitable for processing complex shapes. 3. Wide application range. It can cut various materials, including metals and non-metals. These characteristics make laser cutting an indispensable processing technology in modern industry. The quality and efficiency of laser cutting are affected by multiple process parameters, mainly including 1. Laser power, a key parameter affecting cutting speed and depth. Higher power results in faster cutting speed and deeper cutting depth. For example, when cutting thick plates, increasing laser power is necessary to ensure cutting quality. When cutting thin plates, reducing power can prevent excessive ablation. 2. Cutting speed. The cutting speed is closely related to the material thickness and laser power. Too fast a speed will lead to incomplete cutting, while too slow a speed will increase the heat affected zone. Too slow a speed will cause overmelting, a rough cut surface, widened slit, and melting of sharp corners, reducing cutting efficiency. Too fast a speed will result in incomplete cutting, with sparks spraying randomly. Some areas may be cut through, while others are not, leading to a rough overall section without slag. 3. Focal length. It determines the focusing position of the laser beam, affecting cutting quality and precision. For example, when cutting thin plate, the focal length is generally set near the surface of material. When cutting thick plate, the focal length needs to be appropriately adjusted to the interior of the material to ensure the cutting effect. Positive focal length. Focus above the workpiece surface, resulting in a rough cut surface for thick steel plates. 0 focal length. Focus on the workpiece surface, suitable for thin carbon steel below 5 millimeters, with a smooth upper surface and rough lower surface. Negative focal length. Focus below the workpiece surface, used for materials like aluminum and stainless steel. 4. Auxiliary gas. It assists with heat dissipation and combustion, blows away slag, and enhances cutting surface quality. Insufficient pressure may cause a difficult piercing, prolonged time, slag formation on the cutting surface, and inability to increase cutting speed. When the gas pressure is too high, large melting points are formed, the cutting surface is rough, and the cutting seam is wide. In severe cases, the cut part may melt, failing to achieve good cutting quality. 5. Nozzle. The shape, aperture, and height, distance between the nozzle outlet and the workpiece surface all impact cutting effectiveness. The nozzle prevents slag and debris from rebounding, protects the focusing lens from contamination, and controls the gas diffusion area to ensure cutting quality. Mastering the setting and optimization of these process parameters is crucial for improving cutting quality. To achieve the best cutting effect, we need to optimize these parameters. Common methods include 1. Experimental method. Adjust different parameter combinations. Observe cutting effects and identify the optimal parameters. 2. Empirical formula. Calculate reasonable parameters using existing formulas and data in conjunction with material properties and equipment performance. 3. Simulation method. Utilize computer simulation software to predict cutting effects under various parameters and optimize process parameters. I hope everyone can apply these methods flexibly in practical operations to enhance cutting efficiency and quality. Finally, let's do a few exercises to consolidate what we've learned today. I hope everyone completes these exercises carefully to deepen their understanding of the key points. Today's lesson is over. We've covered the basic principles, classification, equipment components, characteristics, and process parameter optimization methods of laser cutting. I hope everyone masters this knowledge and applies it flexibly in practical operations. If you have any questions, please feel free to ask. This lesson is concluded. Thank you for listening.